Hello, good afternoon. It's a great pleasure for me to be here today, and I would like to thank the organizers for inviting me to have this talk. So, I'm Dhayalan Velauthapillai, Head of Advanced Nanomaterials for Clean Energy and Health Applications. It's a research group at Western Norway University of Applied Sciences, Norway. Um, so, this is Bergen, this is Norway. This is western part of Norway, and my university and my campus, Western Norway University of Applied Sciences, lie here in this city. And we have 7 mountains. You see that around the city, we have 7 mountains. So it's a 7 mountain city. So we have actually 5 campuses in the western part of Norway. My campus is in Bergen, and we have around 16,300 students, and we have 2,000 employees, and we have 4 faculties. So it's a big university. Um, so my research group is called Advanced Nanomaterials for Clean Energy and Health Applications, and we have collaborations with a lot of universities in India as well, and Sri Lanka. And in addition, we have several collaboration in Asian and European, and of course in USA. So we work on advanced nanomaterials for clean energy applications and health applications. So we work on solar cells, we work on hydrogen production, we work on, as far as health is concerned, we work on tissue engineering, and we work on 2 aspects. We work on modeling and simulation of nanomaterials for different applications, and at the same time, we synthesize these materials and we work on, of course, on solar cells and so forth. We work also on floating solar. So recently, we have established the first pilot floating solar project in Sri Lanka with the support of the Norwegian industry, and we do a research on floating solar as well. In addition, as far as energy transition is concerned, there are a lot of work has to be done in energy policies and management. So we have research going on in this sector as well. So we have variety of research activities in my group, and we have students from even from India who come to HVL for research stage, and we send our students to India as well. So we have Norwegian funded projects in India. We work on storage as well, supercapacitors, photocapacitors, and so forth. Okay, then that is said, we will start with solar cell materials. So first of all, we have to talk about the different generation of solar cells, which you are familiar with. So as you all know, the first generation of solar cells are silicon based, and 95% of the market is actually dominated by the silicon technologies, So it's a well established technology, as we all know, and the efficiency is very high, around 25.7, 26%. And as far as modules are concerned, it's a bit low, but it's a well established technology. But there are some challenges with silicon technologies. I will come back to that later on. And the second generation, of course, it's thin film technologies. It's mostly based on chalcogenides, cadmium telluride based technologies, copper zinc tin sulfide technologies, and copper indium gallium diselenide CAGS technologies. And of course, we have technologies, solar energy technologies, solar cell technologies, which are based on compounds of group 3,5 elements, gallium cyanide, gallium arsenide, gallium selenide, and gallium indium phosphorus, and these type of technologies. But in the 80s and 90s, people were thinking of other type of technologies which are cheaper, which can be flexible, and people focused on organic materials. In that sense, as you all know, surely heard about dye-sensitized solar cell. The pioneer behind this dye-sensitized solar cell is Gretzel, Professor Gretzel, and that was in 1991. He introduced this concept, dye-sensitized solar cells. So we have quantum dots. It's similar to dye-sensitized. Only thing is we use quantum dots instead of dyes. And we have organic solar cells. But recently, people have been talking much about perovskite solar cells, because perovskite solar cells in the short span of time, just in 8 years, it has started to convince people that it could compete with the well-established silicon technology. I'll come back to that later. So if we consider silicon technology, as you all know, silicon is a material which is the second most abundant material in the world. But this material has an indirect band gap. So if we compare with CIGS, which is a thin film technology, thin film solar cell technology, if we compare these two technologies, then of course you see that a layer of silicon must be around 10 to the power 4 microns thick to absorb 100% of the light. At the same time, CIGS, that of course, if it's 2 microns thick, that is enough. So what does it mean? Si silicon-based technologies have to be much thicker, you know. So if we want, so there are some advantages with thin film technologies, isn't it? So in that sense, people were looking into different type of thin film technologies, and organic based or dye-sensitized solar cells and these type of technologies, these will be very thin and very flexible. Okay, so as far as silicon is concerned, we are talking about silicon because silicon is the most well-established technology. That's why we are talking about silicon. The silicon material, of course, if we consider the solar radiation spectrum, if the spectral irradiance is 1000 watts per square meter, silicon will use only around 468 watt per square meters. So that is the maximum amount it can utilize, you know. So we must find some other combinations, other materials which could use more fraction of the solar energy radiance, spectral irradiance, you know, to produce electricity. So that's what people were trying to do. So as far as HOMO junction is concerned, the maximum limit is around 33%. So if you see that it's well known, as far as silicon is concerned, if you have photons which have energy more than energy band gap, it will be absorbed, but the rest of the energy, you know, will be wasted. Thermalization, one is thermalization, and if the photons have less energy than the band gap, then of course 18.5% is gone, and recombination 1.5% is gone. Then you have only remaining efficiency is only 33%. This is the well-known Shockley-Coulson limit, and so it depends on the band gap, isn't it? So the optimal band gap is around 1.4, 1.5 electron volts. So you see gallium arsenide, it's GaAs. So gallium arsenide, of course, so that is the best element for the time being, but perovskite structures, they have also band gaps around 1.55 electron volts. And the other thing is, as far as perovskites are concerned, these new materials, the energy, the band gap can be engineered such that you could do some techniques, you know, tricks to manipulate with the band gap. So that is another possibility with perovskites. Yeah, so there are advantages with silicon solar cells, but the disadvantages is that it is brittle, very thick, expensive, and there are a lot of waste. There are a lot of energy is used to produce these solar cells, and you need 99.9999%, isn't it? 99.999% purity, isn't it, as far as silicon is concerned. So there are some disadvantages. So in order to, if you want to have some technology which is flexible, very cheap, and you can use anywhere, it is affordable even to poorer families, then of course it's better to go for new technologies. So in that sense, even thin films, there are some problems with thin films, CIGS, cadmium telluride, there are health risks, environmental risk, safety risk, so there are risks, and the efficiency is not that high either. Recently, you can have a look, this is from 2020, so there are some changes now. But if you look at this here, so I'll just point it out here. So you see here, as far as silicon is concerned, it took nearly 30 years to come up to these, this level, 26.1% now efficiency, but it took many years to come to this point. And look at CIGS, even that took a lot of time. Here, look at quantum dots, dye-sensitized solar cells. Look at dye-sensitized solar cells from 1996 to now. It's still around 12% efficiency. Nothing has changed. But look at perovskites with black marks here. Just from 2013, 2015 to now, it has come around. This is from 2020, but now the last efficiency recorded is 25.7%. So it is increasing rapidly in a span of just 8 years. Okay, in 2008, the efficiency was around 3.5% or something like that, but now it's 25.7. So a rapid increase, and look at the interest as far as the published articles are concerned. In 2008, the first solar cell with perovskite was published, only one article. 2009, I think, and in 2010, nothing. 2011, another paper, and 2002, a few papers, one or two. Then from 2013 onwards, there is a rapid change, exponential increase, in papers. So how these perovskite solar cells emerged into the field? Actually, perovskite was discovered long time ago in 1839, but Lev Perovsky is the first man to work on perovskites, in different type of applications. So as far as solar cells are concerned, Professor Miyasaka is the first person to use perovskite material in solar cells. But the concept is based on Professor Gretzel's, dye-sensitized solar cell technologies. So instead of dyes, because dye had problems with stability, so Miyasaka used perovskite instead of dyes, in a dye-sensitized solar cell. And he produced an efficiency of 3.8%. And in 2011, Professor Park, he used the same, same material, same structure, but he used a more concentrated perovskite material, and he got 6.5% in 2011. But he had a problem. He was using electrolyte. So what happened was, this perovskite material, it got dissolved in electrolyte, and it vanished. So he was thinking of using something else for electrolyte. Then he got an idea. It's an old idea actually. Gretzel was using. He was trying with some organic materials before, Spiro, and and PARC, he used instead of electrolyte, he used Spiro. So this organic material helped him to reach an efficiency of 9.7%. Then everything started. Then people got interested in perovskite material, and Professor Henry Knight is another legend in this field. So now he has been working on different type of perovskite material, and he is also combining this the perovskite material with the well-established silicon technology, and he has his own company now, and they are going to market silicon and perovskite combined tandem cells in 1 or 2 years, I heard. Okay, so there are many others who are working on perovskites as well. What is perovskite? Perovskite is simply a structure ABX3 formation structure. It will be like this. There are two cations. It's well known. One is here, of course, we have been using, most of the people have been working on methylammonium lead iodide perovskite, CH3, NH3, PbI3. So you see there is a CH3, NH3 plus organic cation, and you have a Pb2 plus inorganic cation, and you have the halide iodine anion. So in that sense, it's a hybrid structure, organic inorganic structure, and instead of dyes. So how it is used in a solar cell? Yes, of course you have an absorption layer. Absorption is the important thing as far as solar cells are concerned. The material must have good absorption. So that is the important thing, isn't it? So you have to absorb the photons. So that is the important thing. So light passing through the transparent electrode, the green one here, so what happened? It goes through the photosensitive perovskite material here, and it stimulates excitations called the electron hole pairs. And what happens? Electron goes through the dense TiO2 layer, and it goes through the electrode, whereas Ho plus, it goes through, we call it hole transport layer. It goes through hole transport layer and to the counter electrode. So here we can use a lot of materials for electron transporting layer. We can use titanium oxide, you can use SnO2. I'm sorry, it is not here, but we can use SnO2, and active layer, of course, it will be perovskite. It's absorption layer, and you have the whole transporting layer. Here, of course, we could use Spiro. That is the most used one, but the thing is, it's very expensive. So people are trying to use inorganic materials. Even people are trying to use carbon-based materials. And you have the counter electrode, that is platinum. Mostly platinum is, I mean gold is used. So this is the structure. So the main thing is the perovskite has an absorption which is very good compared to silicon. And here you see the band gap is around 1.55. So that is the optimum value, for solar cells. So CH3, NH3, PbI3, it has a band gap around 1.55. Okay, so why perovskite solar cells? Of course, perovskite solar cells have, perovskite materials have very good absorption coefficient, small and tunable band gap energies, long carrier lifetime, high charge carrier mobility, and diffusion length is high, and binding energy, excitant binding energy is very small, and open circuit voltage is around 1.3 volt, and efficiency now it's around 25.8%. So this is remarkable. So if you compare with the silicon based solar cells, you see that as far as price is concerned, it's very less compared to silicon, and the efficiency is almost the same now, but the problem is the stability. So it can't last for more than 1 year for the time being. So that is the biggest problem. So we have to work on it. But perovskite, as far as here, of course, the key, the graph below is the open circuit voltage compared to the band gap for a range of technologies here. And it demonstrates how much of photons energy can be utilized by different technologies. You see that perovskites is around 70% compared to, for example, organics solar cells. It's less than 50%. So it can compete with silicon solar cells because it has high photon utilization efficiency. Okay. So if you compare with the other technologies, perovskite had the best characteristics or best performance as far as materials cost is concerned, fabrication cost, energy payback period, efficiency is good, compared to other technologies. So what are the challenges? Yes, the challenges are, of course, long-term stability and lead, toxic nature of lead. We all know that if lead comes into water, then it could poison the water and it might harm. It will give health issues, health problems and environmental problems. And mass scale production is another problem. But there are so many opportunities with perovskite solar cells. You could have tandem structures such that you could absorb the whole solar spectrum, and you could boost the efficiencies if you can, and you can increase the stability if you can make it two-dimensional perovskites, and you can use carbon materials, so you can reduce the cost. So we can combine with other technologies, silicon technologies, and even with thin film technologies. So it is compatible with other technologies. And perovskites have other areas, application areas. We have been working on perovskites for field effective transistors. So that is of interest. Here it shows the PCE evaluation of perovskite solar cells for the past 4, 5, 6 years. And you see not only the traditional hybrid organic, inorganic perovskite solar cells, but just inorganic solar cells. For example, CSPBI3 is also of interest, and you see they have got some good efficiencies here as well. So CCM based perovskite solar cells, and even you could have the HTMs. As I mentioned, Spiro is mostly used, but you can, instead of Spiro, you can use inorganic HTMs, for example, the blue one. And here they have got up to 20.4% efficiency. So there are so many possibilities with this type of hybrid, organic, inorganic, and this type of stuff. Okay, just run through. So you can use, for example, carbon materials. So carbon materials can be used as HTM. They can be used with ETL layers. They can be used with perovskite layers. And so these type of things, of course, people are trying, and our group is working on these as well. So the problem is the toxicity of the lead halide perovskites. So we have to work on it. Although there are so many advantages, so we have to maybe substitute lead. So that is one of the things. So people are working on that as well. So tin based, people are using tin instead of lead, germanium, bismuth, SB, but still, tin based is okay, but the problem is again the stability with tin based. Lead is the best for the time being. Lead based perovskites are the best solution for the time being. Okay, so people are working on other structures, because why? The stability has to do with the methyl group, the organic group. So instead of organic group, people could work on inorganic structures. So we can substitute the organic cation by inorganic cation. So for example, here you have a compound which you call it CS2AgBiBr6. So it's a double perovskite material. So it's inorganic material, but you see the efficiency is very low. We have been working with this material as well, but it is very low. Recently, they have reported an efficiency of more than 5%, but it is still very low. But it's more stable than methyl ammonium lead iodide perovskites. Okay, I will just in future, actually, we have to work on different type of materials. Instead of lead, we could have first group elements, M plus elements combined with M3 plus elements. So instead of lead, we can have M plus, M3 plus combined together. So there are so many things we could do, and we are working, our group is working on numerical simulation as well, study these materials in detail and find some new materials which can be used for solar cell applications, and this can be synthesized later. So tandem perovskite solar cells, that is I think it is going to be commercialized as soon as possible. So it might edge towards already around 29% efficiency. So it is going to edge towards 30% efficiency. So this is the structure. You will have both silicon cell, one silicon cell, and top of it you have the perovskite cell. So you can have 2T junction, you have 3T three junction, you can have 4 junction. These type of technologies is going to be the future. So what happens here? The perovskite cell act as a top cell absorbing the visible light, while a solar cell with a narrow band gap, for example silicon, acts as the bottom cell and harbors photons in the near infrared part of the solar spectrum. So you see the whole spectrum will be utilized and the efficiency can be increased. So this is going to be the future. So a lot of companies are working on perovskite solar cells nowadays. Space mission, okay. Stanford University has been working on producing modules. And Swansea University, they have produced modules, with efficiency 6.6, 6.3%. And there is a company, Microquanta Semiconductor. They have reported that they have already produced a module which could have efficiencies up to 18%. Okay. And Saul Technologies in Poland, they are working on inject printing of perovskites. So this is easy to make, isn't it, from inject printing? So it will be faster to produce a solar cell, perovskite solar cell, compared to a traditional silicon solar cell. It may be 4 times faster. And you could have perovskite, 2 perovskite structures with different band gaps to absorb the whole spectrum of solar spectrum, the whole solar spectrum, such that you could increase the efficiency. That is another possibility. Oxford PV has set a world record already, okay, for perovskite solar cell. And what is the future? In future, we have to work on 3 things, or 4 things. One is the efficiency. There, of course, we have to work on interface between ETL, absorption layer, and HTL. So interface engineering is one important thing, and we have to think about the transport layer design. So that has to do with efficiency. And as far as stability is concerned, we have to get rid of these organic cation. We can have another inorganic cation. We have to try with that, and we must use some additive engineering and this type of things. Cell encapsulation. These are the things we have to work on as far as stability is concerned. Lead-free device, as I mentioned, we can try with tin based and combination of different materials. That is another thing which can be used. And of course, tandem devices. This is going to be the future, and you're going to hear soon. There will be a commercialization of silicon perovskite tandem device in the market. So you're going to hear a lot on perovskites. So thank you very much. Thank you.